Welcome. If we look at the differential geometry of a finite geometry, we want to connect 2 points. Like Hopf-Rinoff, we want to connect 2 points with a geodesic. That is not possible if the geodesic is defined locally by a dynamical system which is locally defined, right? So because we have only finitely many directions in which we can go, so we have no chance to reach every point if the space is, large enough. So that's motivating to look at more general frameworks also for the geodesic flow. The Huygens principle, which you have in physics, motivates to look at waves, right? Waves are connected to geodesics, and the front of a geodesic flow is associated to the wavefront of an electromagnetic wave in classical physics. So let's look at the wave equation. There are different frameworks, depends on the Laplacian. The most obvious one is to look at the Laplacian coming from calculus, from exterior derivative. So then we have a very simple framework, finite matrices, n times n matrices, where n is the number of points in this geometry. And then we have also kind of the cohomology you can read off from the kernel of these blocks of the Hodge Laplacian, and solutions of the wave equation can explicitly be written down. A little bit simpler is if you take the connection Laplacian, which is the square of the connection matrix. I introduced that in 2015, 2016, and the nice thing is, and what really make me excited about all this, is that this matrix is unimodular. The determinant is 1 or minus 1, explicitly given by the number of odd-dimensional simplices. And then you can also look at the wave equation here. The nice thing is this, because it's invertible, this solution is now true unconditionally. We don't have to restrict ourselves to the autocomplement of the harmonic functions like in the case of the Dirac matrix. So this is very nice. Of course, D'Alembert in 1747 did not look at this framework like this. He didn't have, he looked only at one-dimensional framework, and his solution together with Taylor, it's a superposition of 2 transport equations, which we can see also here, right? So these are 2 Dirac type equations, 2 Schrödinger equations, if you think about D as a, operator in quantum mechanics. So these are Schrödinger equations, and then these 2 solutions, one for particles and antiparticles. This together gives us a very nice relativistic framework, and that also works here. And the solutions can be written down explicitly. You don't need any theory, like what we learn in linear algebra is the Fourier theory. We can do this all with writing down the eigenvalues, eigenfunctions, and diagonalize it and solve these ordinary differential equations and write down explicit solutions. That's the Fourier method, but what I'm actually aiming for is to connect one point with another using a wave, and this problem cannot be solved so easily using the Fourier method, the eigenvalue method, the spectral method, but it can be written down explicitly when we have the D'Alembert approach. It's the operator method which we learn in linear algebra courses. So all this is approachable for a student who has seen a few weeks of linear algebra, so matrices and self-adjoint matrices. Over the break I was looking at the problem again. I have looked at this before, but now kind of revisited it, and what we have is for every point x we have a basis vector ex and we have a basis vector ey, where the wave is ex is the wave located here and ey is the wave located here, just localized. And now the question is, can you find an initial velocity for the wave such that it really focuses again, at time t equal to 1 here? And the answer is yes, you can do that. It needs some assumption so that you can do this. What we need is that globally we need just to scale the operator so that we can then solve for the initial velocity here. And you see that here, just as the proof is just everything is explicit, we can write down this solution. We want to have EY is the solution at t equal to 1, and so now we just have to solve for v, and we can write down this v. But you see that we need actually to invert the sign of CL. CL better doesn't have eigenvalues, which is a multiple of pi. You can achieve that, for example, by putting the c, making a small enough c, Planck constant. If you want, you introduce a constant here to make this all work. And then we have an interpolation, and it even works for x equal to y, right? You can even take this solution for x equal to y. It's a wave which started x and comes back. Of course, you could also take t equal to 0, but it's the first time the wave kind of comes back to itself. We don't actually need a small c, we can also take a larger c. The only thing is we need the sign of CL to be invertible, or the sinc of CL if you want. So that's the kind of remark which I worked on over the Thanksgiving break, because I'm teaching differential geometry, a little bit about the differential geometric aspect of this. So what you can do is you can think about the wave solution as a curve in Rn, right? Rn, n simplices we have, so the Hilbert space is an n-dimensional space, so we have a solution in that Hilbert space, which is a curve. And so what we have seen is kind of, if you look at that, we have a point Ex and we have a point Ey, and there is a curve which connects Ex with Ey. A relatively complicated curve in general. I can show you pictures. You can also connect Ex with Ez. You have a triangle, and you can do that, and then what we have is a two-dimensional plane spanned by these two vectors. The initial condition which goes to y, the initial condition, initial velocity which goes to y, the initial velocity which goes to the simplex z. So we have a kind of a triangle defines us now a two-dimensional plane, and then we can look at the unit circle in that plane and start in each of the directions and see what surface we get. Yeah, surface which in general becomes very complicated over time. I mean, you can see that here, right? If you have in this case, this is a maybe simplicial complex, it's a path graph with, so this gives us paths in a 24-dimensional space. We have a curve now, given the initial condition and an initial velocity, I get a curve which is in a 24-dimensional space. It's moving in a 24-dimensional space. And if you look at that, this solution, it's not the obvious solution. It becomes very complicated. These exponential maps, also in differential geometry, become very, very complicated. But locally, we have just a nice surface. We can study properties like curvature. Now, we looked mostly at surfaces in R3, so of course I take the smallest case of a simplicia complex where the Hilbert space is three-dimensional. So we have three simplices for this simplicia complex here, and this three-dimensional space now harbors a surface, and it's the image of the exponential map. So I use the lemma here and interpolate from x to y and from x to z, and I look at then all the possible waves which go, and then this gives a surface which is rather complicated already in R3, and it's nicely immersed, but then it's only embedded, it has half intersections, it becomes very, very complicated. The curvature can become negative and positive. I looked at that, and it's no problem, just because we have explicit solutions, to get the parameterization of these surfaces. In this case, I measured also the curvature using just the formulas which Gauss gave, right? The determinant of the shape operator. So compute the kind of discrete versions of the first fundamental form, second fundamental form, and then compute the determinants and numerically compute this curvature. So in this case, we get the positive curvature case. Now, this is completely unexplored. What are the relations between, if you have an arbitrary simplicia complex and you look at all these curvatures, sectional curvature notions, Does this have any relation with the curvature which you have when you look at it in a discrete way? Completely unexplored, but it's an exciting topic. That's it for today.